In this video, we're going to look at several spectra that have graphical data instead of the textual data that we've seen on previous videos. So let's look at compounds E and F. They both have the same chemical formula, C4H8O2. So let's look at the HDI of these compounds. So 4 times 2 plus 2 minus 8 all divided by 2. That looks like it gets us to 2 over 2 equals 1. So we have 1 HDI. And that is confirmed by the IR as well, because both of these compounds appear to have a carbonyl in their IR spectrum, 1743 and 1730. So let's focus our efforts on compound E. I'm going to just draw a carbonyl up here to remind myself that we do have a carbonyl. And then we're going to look at the 3 signals in the proton NMR. You'll see that these 3 signals do not have integrations that look like 1 hydrogen or 2 hydrogens or 3. They're simply some numbers that the computer measures essentially the height of this curve. This is the curve that we use calculus to derive, and that is showing us the value or the area under the peaks. You can see how these peaks have some area to them. It's actually rather slight, but they do have area. We measure that area, and that's where we get the integrations from. And so this is actually an integral curve, and you can see that this curve is a little smaller than the 2 curves at 2 or 1 ppm. And so now we're going to come up with a ratio that makes sense and that uses whole numbers between these curves. So I would propose that the curves are the integrations at 2 and 1 ppm are probably the same, and thus the one at the integration of the signal at 4 is less than the first 2. And as we've been saying for a while, signals at around 1 or 1.2 ppm typically are methyl groups. So this is probably a CH3. We do have 8 hydrogens in our formula, so most likely we have a 3 to 3 to 2 ratio, and that makes sense because 23 is close enough to 2/3 of 30 or 29. So these are probably the ratios we have, 2 to 3 to 3. And that tells me that I have a methyl group right here, and we can see that it is a triplet, so that means it's adjacent to a CH2 group, and we do have a CH2 integration or signal at 4, which is a quartet, which tells me that this signal, the hydrogens in the CH2 that form this signal, are adjacent to a methyl group. So this is very indicative of an ethyl group, probably connected to an O, because the CH2 is so far downfield. So most likely I have something like that, where there's another thing on the other side of the O, but I have an O ethyl group in my molecule. And that makes sense because I do have a second oxygen. I've already used 1 in my carbonyl, but I have a second oxygen, so most likely this is an ester. And that leaves me with a single carbon left, I believe. 1, 2, 3. I have 4, and I have not accounted for this 3 hydrogen signal right here, so most likely that is a methyl group, and that would complete the formula, and it looks like I have a complete structure here. That is probably the best structure for E. Moving on to compound F, we have the same formula, the same HDI, and it appears that we have 3 signals, much like we had before. And you can see that these 3 signals are, again, in the same approximate ratios, 3 to 3 to 2. Another big clue is that these 3 signals are all apparently singlets. They do not have any splitting patterns to speak of. So we have 3 different hydrogen regions that are not adjacent to any other hydrogen regions. So that makes it a little more interesting to solve. You'll see that we have the 3 hydrogen singlet at 2, just like we had on the previous question. So most likely we have a methyl group next to a carbonyl. 3 hydrogen singlets at around 2 are very indicative of the methyl ketone or methyl next to a carbonyl, as I have drawn in green here. And then I have my 2 hydrogen signal. Again, it's a singlet. It is still out at 4, so it's probably still next to the O, but it is not next to the other methyl group. The only way to do that would be to have my CH2 right here, then have O, then have the methyl group. And so let's confirm that this methyl group is makes sense in this case. So it would be a singlet. We would expect it to be further shifted downfield to the left compared to this methyl group, which is not next to an O. And indeed, this methyl group is shifted only to 1.2. This methyl group here is shifted to about 3.4. So that makes sense because it is next to an O, whereas this methyl group is only in the vicinity of an O. It is not directly attached to an oxygen. So I believe that this is our compound F. Let's take a look at compounds H and I now, and they have a new formula, C8H11N. So now we have a formula with a nitrogen in it. Again, the first thing we want to do is calculate the HDI. So that's 8 times 2 plus 2 minus 11 plus 1 for the nitrogen, because having a nitrogen present actually increases the allowed number of hydrogens by 1. So we add 1 for every nitrogen. Again, divide everything by 2, and we get 16 plus 2 is 18, minus 11 is 7, plus 1 is 8, divided by 2 is 4. So we have an HDI value of 4, and that's a pretty good indication that we have an aromatic ring. It's not 100%, but it's a pretty good indication that we have an aromatic ring. The other indication is observing that we have IR absorptions just above 3000, 3026. That is a very good indication that we have some hydrogens attached to sp2 hybridized carbons. We also see that we have some what we call aliphatic hydrogens, which are hydrogens attached to sp3 type carbons. That's pretty standard. And then we have these peaks down here. They may have something to do with the nitrogen. Remember that NH absorbances on the IR oftentimes occur in the same region as OH absorbances. So these could have come from the NH absorbances. So let's look a little more carefully at compound H. We see 4 hydrogen regions. Here's the NMR region. So that again confirms that we probably have an NMR group, or an aromatic group. And then we have these 3 regions, 2 hydrogens, 2 hydrogens, and 2 hydrogens, a pair of triplets, and a singlet. So these pair of triplets must be next to each other because a CH2 that is a triplet has to have a neighboring CH2, and that neighboring CH2 would be split by the first CH2. So this is a group of CH2s that are adjacent to each other, and this is 2 hydrogens that are on somewhere else that are not being split by anything. So in this case, I think we have the aromatic ring, and since the aromatic protons integrate to 5, we can make the conclusion that the aromatic ring has 1 substituent on it. We know that we have a set of CH2 groups, so I like to think about that kind of like this, where X's are a group that does not have any hydrogens on it, and I shouldn't put that X up there because that group may have hydrogens, but I'll put a Y here. And then we have this group, which is most likely, the NH2. Let's count our carbons and find out. I have 6 here, 7, 8. I've accounted for all 8 carbons. I've got 5 hydrogens here, plus 4 more is 9. I'm missing 2, that's what these 2 are. So most likely, this is an NH2 group, and that has 1 bonding partner. And so I think I can put these together because I have something with 2 bonding partners. I have a piece with 1 bonding partner and another piece with 1 bonding partner. So I'm going to erase my Y and just fill in the rest of my molecule. So I think this is the best structure for this NMR data. I have a triplet here and a triplet there, and the NH2 sometimes will split with neighboring hydrogens like we have here. We might expect that NH2 to be a triplet, but in this case it appears that it's hydrogen bonding with a lot of adjacent NH2 groups, and we don't get the splitting pattern of the hydrogens that we might otherwise expect. And that's pretty common with OH and NH groups. So I'm not surprised that the NH2 signal is simply this slightly broadened singlet. That is not unusual. So this is probably the best structure for compound H. Compound I would have the same molecular formula, would have the same HDI value, and as we see from this signal at about 7.3, probably also has a benzene ring that is mono-substituted. So let's go ahead and draw that in as one of the pieces to our puzzle. I'm going to put a Y here again, indicating that I don't know anything about Y, but I know that there's only one substituent on my aromatic ring. If I look at the other signals, I have a 1 hydrogen quartet, so that is probably a CH that is adjacent to a CH3. And that means I have two groups on the CH that have no hydrogens, because I know that this H is split into 4 peaks by the adjacent methyl group. So these two X groups do not have any hydrogens. So that is the signal for this hydrogen here. And then I have what looks like two signals very close in chemical shift. A 2 hydrogen looks like a singlet, and then a 3 hydrogen doublet right here. This 3 hydrogen doublet is very likely that methyl group, because we would expect that methyl group to be a doublet. It's only adjacent to one H. And thus the 2 H's that are remaining most likely is another NH2 group. So now I have all my pieces laid out. I have one way to attach an NH2, I have one attachment point on my benzene ring, and I have 2 attachment points on this group here. I don't know what to call it, but I think I can draw my structure now. So here you see I have my CH that's adjacent to 3 hydrogens. It's split into a quartet. That's this signal here. This hydrogen is this hydrogen. Then I have my methyl group that is split into a doublet. That's that signal, and that's that group that I drew initially. And then I have my NH2 again, that is a slightly broader singlet. Again, we're not getting a lot of splitting with this NH2, probably because it's hydrogen bonding with other NH2 groups in this sample that's in the NMR spectrometer. And then I have my mono-substituted benzene ring right here, and I think this is the best structure for compound I.